x direction. In the x direction, what does it tell us? It tells us that force hinge x, right, which is going to the right, and then that nothing from the y component of the hinge force, nothing from the gravity acting on the beam, nothing from the downward force from the mass of the weight. But there is a non-zero contribution from the tension. Oh, sorry. What did I say? Oh, yeah, I'm doing x. Yeah, there is a non-zero contribution from the tension. There's a positive or negative in the x direction from tension. Negative. That's good because we know it better be going to the right with this guy, so it doesn't better go to the left. So it's minus tension times the geometrical factor. I think it's cosine of phi, as I defined phi up there. But straighten me out if I've got that backwards. This equals mass of the beam times a in the x direction. Oh yeah, but the center mass is moving the beam, no acceleration. So that's all zero. Great. So right away now we've got an expression for the x component. Oh, I see. I see why. I was saying, oh, this is the thing we need now. So that's why you guys were all saying you do the next direction. Yeah, you were telling me what I meant to ask, not what I actually asked. Great. So now we've got that, and that's an okay answer because we've already solved for the tension. But if we hadn't solved for the tension yet, we'd need another equation. But we've already solved for the tension. It's up on the top. So this is interesting. You can plug that in and see what the dependence is on all these things. So what do we get? We get t times cosine phi, right? And what is that? It's just cosine phi times all that. So I got mass of the beam over 2, and I get the mass of the weight, right? And I get what? G, and then I have cosine over a sine. Cosine phi over sine phi, which is, what is that? Cotangent? Yeah. I think it is. 1/change. Doesn't matter though. I can do it like that. So does this make sense? First of all, we have the right units. Let's see. I want force. This is mass times an acceleration. This is unitless. 2 is unitless. Yeah, it looks good. But think about the physical interpretation here. What this is telling me is that the x component of the hinge force depends on the mass that I hang on the end, and it depends on the mass of the beam. Does that make sense? Let's think about that. So I'll go back to my prop here. If I increase the mass over here and push down, or whatever, throw some mass on so gravity is pushing down on that mass and therefore exerting more downward force. That does make sense, doesn't it? Like, suppose this thing were, suppose I kept pushing. If this were a strong enough cable and I pushed down hard enough, what's going to happen over here? I'm going to break this thing off. It's going to go that way because I'll be exerting more and more force in that direction by pushing down over here. So it makes sense that the horizontal component of the force of the hinge acting on the beam over here has to increase if I increase the weight that's hanging over here. But let's take a look at the y component of the force. So if I increase the weight over here, if I increase m sub w, does it affect the y component of the force of the hinge on the beam over here? It doesn't. It's sort of surprising at first thought. Is that right? Because it seems like if I'm adding more downward forces in the problem acting on the beam, it seems like I should increase upward forces somewhere else to compensate for that. And that is what's happening. It's just that it's not happening over here. It's happening somewhere else. What goes up? What upward force on the beam increases if I increase more weight down here? Tension. This goes up. See, the thing is, this weight is connected at the same place where this cable is connected to the beam. So that means if I keep adding more and more weight here, this guy's doing all the, this is what's exerting the force to counter that. But if I add more weight over here, if I increase the weight of the beam, now I need to have more upward force over here and more tension. That's why so F H sub HY, right, the vertical component of the force of the hinge on the beam, that goes up with MV, right? It equals MV times G over 2. So the bigger I make, and notice it's over 2. Why is that? Because only half of that weight gets picked up over here. The other half gets picked up over here. So the tension gets bigger if I make the beam heavier, and the upward force from the hinge on the beam over here gets bigger. They share the weight. Why do they share it? Why is it divided in half? Because the weight of this thing is it's as if it's all acting at the center mass of the beam, and that's halfway between these two places. Just like if I'm carrying something with somebody else, and we're both carrying some big heavy load, like this long, I don't know, I was in construction for a while, we used to carry lumber around, right? And on the other side, we both keep holding lumber up. Well, if we're both at the ends of the piece of the lumber, we're sharing the weight, right? As long as it's not a piece of wood where the density is changing, or thicker on one side. In that case, okay, whoever's on the thicker end has got the bad end of the deal. They have to exert more force to hold it up, right? But if it's uniformly distributed, then you're sharing equally. Now, if you don't want to share equally, what you do is you walk in a little bit. So who's paying more? Who has to lift more? The person who's toward the middle of the beam, or the person who's at the other end? Who has to exert a greater upward force when carrying a piece of lumber? The one who's not all the way at the end, or the one who's all the way at the end? Who needs to exert a bigger force? So suppose you stood right, suppose you were by yourself, you had to lift up the wood. Where would you stand? In the middle. You're on the end, it's just going to fall down on the other side. So the person who's in the middle is carrying all the weight, right? And then if he goes on the other side, well, all he's doing is just doing nothing. He's got to keep his hand on top if he wants, right? You learn this the hard way when you carry lumber around. And so you move out a little bit like that. Okay, now something has to be on the side of support, but they don't have to lift it that much. Until you get all the way to the end, now you're sharing equally. So if you're more toward the middle, you're doing more of the support. I was going to say more of the work, but it's not work if it's holding still, so I be careful how I use my terminology. So the closer you are toward the middle, if I tied this, in other words, if I tied this cable more toward the middle, it would be doing more and more, it would be supporting more of the mass of this thing. And then you would need less upward force over here. Anyway, it's worth thinking that through. It's kind of surprising sometimes. When you have problems with when you have static equilibrium problems, it is surprising sometimes where the forces get distributed. And you'll see some, like on the midterm from last semester, second midterm from last semester, that's a couple of, it's pretty, pretty tricky midterm. It's got some stuff on there like that. And if you know how to think about it, it might help you when the equations don't go the way you expect. Yeah. To get the total, oh right, so the question is, do I need to use a Pythagorean theorem or should I use that? If the question that's being asked is what's the magnitude of the total force that the hinge exerts on the beam, yeah, then you can use Pythagorean, you'd say, it's the square root of fhy squared plus fhx squared, right. But if you're asked for the vector, so if the problem says what's the vector of force of hinge acting on the beam, well, I think it's perfectly valid to give the answer in terms of the components of the vector. And I'd say, okay, well, fhx equals this, and fhy equals that. That specifies the vector. But it's a good question. So it depends on what you're asked for. I was just using a shorthand notation up here, and I was saying, tell me what the components of the vector are, or tell me what the full vector is. So I think it would be full credit in this problem just to state what the components, as long as it's clear from your diagrams and from what you've written, what the directions are for your components. If you don't have axes drawn on your picture, they don't know what x and y are, you must sort of get credit for that. But, and in fact, if I ask for the vector and you tell me what the length was, you need to have the length right. So, oh, it's 17 newtons, right, is the force of the hinge acting on the beam. If you don't say the direction for it, then you wouldn't necessarily, chances are you need to specify that, either by giving the angle that it forms with respect to a horizontal or vertical or something like that, or by giving me the components, right? And the easy way for these problems almost always is to give the components. That's how I chose to do it here. Yeah. Yeah, cool. All right. Great. And so sometimes in a problem, too, in the description, to figure out what direction the forces are allowed to point, you have to look for clues in the way the problem is written. For example, if you have a frictionless wall, suppose you have a problem like this, the fact that there's a hinge here tells you that the force can be in either direction. Actually, if we're nailed to the wall, that'd be true as well. But suppose you have a problem where there's a frictionless surface, a wall. There's a problem like this on the last midterm, on the last semester's, like some 2012 midterm 2 problem, where there's a frictionless surface in the form of a wall, it's a vertical surface, and there's something resting against it. Well, if it's frictionless, you know, right? Is the force going to be totally horizontal or totally vertical? Totally horizontal. For the same reason that a frictionless surface is horizontal, it's like this, horizontal surface, then if you have a frictionless surface, the only force you can get is a normal force, that's vertical. Well, the whole thing on like this, it's the same situation, just sideways, right? The only force you can get is that way. So that's an important part of the problem, to figure that out so that you don't So you don't go solve for some vertical, you don't have equations to solve the problem. If it could have exerted a vertical force, maybe you don't have enough constraints in the problem to actually nail down an answer for the other forces in the problem. So pay attention to stuff like that. Okay, great. So in this problem, we actually solved this in a funny way. We just chose different pivot points and just used, well, for up there, up into this last part, we used different pivot points and just solved for Newton's second law for rotations. And that got us 2/3 of the way to the problem by itself. There's a lot of ways to solve a problem like this. The way I normally would do it is by doing x and y Newton's second law, and then choosing one pivot point and doing Newton's second law for rotations. But you can do any way you want. You have a lot of freedom, which some students like and some students do not like. They prefer to say, no, here's the formula. Always do it this way. So if you want a formula, I would say do x and y Newton's second law, and then you have to make one decision. What pivot point do I want? And if you want, okay, always choose the center of mass. I guess it's possible I could design a problem that wouldn't work, but chances are that'll work. And if it doesn't, then just choose another pivot. Anyway, okay, great. So this is all about sort of architectural kind of stuff, right? But there's other cases where there's so a lot of the pre-health people in here like to have some anatomy stuff. So in our bodies, for most people, certainly for me, what is the most toned muscle in our body? Sorry? I'm getting lots of answers, but I'm not sure what the heart. Well, yeah, maybe. I guess. So how about skeletal muscle though? Bicep? Yeah, bicep. That's me. It's bicep. What else? It's my favorite muscle to exercise. It's my masseter muscle. Where's the masseter muscle? Yeah, it's right there, right? Yeah, here's the masseter muscle. All right. So let's think about how we use the masseter muscle. See if I can get this to work. Oh, I have this stick up here. I don't want it to fall on me. Oh, too backwards? No. It's a hard demo. All right, so the masseter muscle, right, is what connects your jaw to the rest of your skull. And you use it to eat. I love to eat. So it's an important muscle to have, and we all use it a lot. That's the thing. That's why I think it's toned. Oh, geez, I can't get this to stay up here. I want this to stay so it doesn't fall over. Because I want this guy to chew a carrot. That's what I want to do. I want to talk about, so why do you chew carrots in the back of your mouth? Why don't you chew them in front of your front teeth? So that's an interesting answer, right? Partly it's because the front teeth aren't made for chewing carrots. They're too skinny. Right? They'll slice up a carrot. They won't grind it up. But that begs the question, well, then why over evolutionary time do we have those teeth in the front of our mouth? Why didn't we put those? Hope this doesn't fall on anybody. See, that is the masseter muscle, right? And look, there's a hinge up here, right? See that? Yeah. Huh? You're learning a lot of anatomy in this class. And I'm going to show you, we usually have a carrot up here. I'll just use this. Okay, so, all right, so if you're going to chew a carrot, you could do this, right? But you're more likely to do this. And it's partly because the teeth back here are flatter and they're molars, right? You can grind it up better. But why over evolutionary time do we not develop molars up here and then those thin, skinny teeth back here, right? Well, maybe it has to do with torque. So let's calculate that and see. Let's calculate that. So let's think about it. This problem actually is very similar to one that we've talked about already a little bit, and you've already got homework problems that look like this, that look like a teeter-totter. So if you have a teeter-totter, right, and you put a fulcrum, I suppose I have a giant boulder over here, and I have a little guy over here, and I want to support this boulder on the other side. Where do I put the fulcrum so this is going to be in static equilibrium? Do I put the fulcrum over here, next to me? Well, I'm not getting a strong response. No, it's me over here. That makes more sense, right? And why? Because there's a big force due to gravity on the, mass of the boulder, of the rock, right, times g. That's much bigger than, my weight, so mass of me times g, right? And so why does that work? Oh, it works because this guy's a smaller radial arm and a bigger radial arm. So the torques are balanced, right? So if we say, let's take this as our pivot point, the fulcrum, and say, how do we balance the torques? Well, if this is my positive direction for rotation, am I exerting a positive or negative torque on this thing? Positive, right? I'm pushing down over there, it makes it want to go that way. And it's negative over here. So if I calculate the torque from the rock, right, it's going to be a big thing, mass of the rock times g times a little distance, this little distance L, right, compared to some big distance, capital L for me. And it's negative that, and it's positive, and then torque to me, right, is positive mass of me times big L. So, I get a g in here, don't I? I put a g, but I can barely read it. It's a big G. Yeah, so that's the idea, that we have equal and opposite torques. In the same way we can have equal and opposite forces. And the way we achieve that is with a small distance and a big distance, big force and small force, and it all works out, right? So the ratio of these distances is the ratio of forces. Well, the same thing's going on here. It's just that the fulcrum and the sort of natural place to choose the pivot point isn't at the middle of the beam, it's on the end of the jaw. It's that hinge over here. So, right, the hinge over here where the jaw meets the skull, if you think of that as the fulcrum, right, so we got some jaw, right, with teeth, right? I'm giving myself a lot of room. Oh, no room for a skull. That's too bad. Anyway, all right, so you get the idea. You got some guy up here, he's no longer with us, but his skull survives. And, all right, so, and here's his jaw, right? And all kinds of funny things back here. It's fun to draw a little, Anyway, okay, so this guy, there's his mouth. If we put the carrot out here and say, well, here's the hinge, right? So here's our pivot point, right? And here we put the carrot way out in the front, sort of a bad place to put it. How much force can we exert on the carrot? Well, what are the forces in the problem? Let's make a figure diagram for this jaw, okay? And there's a couple forces acting on this jaw, right? There's a masseter muscle. Masseter muscle, actually I didn't draw this, but actually it really does this. Anatomically, the jaw comes up further than I drew it. The teeth come further back too. So this is our pivot point up here, but we're going to approximate it as a one-dimensional thing. We're just going to say, all right, here's the jaw. All right, and we're going to say, here's our pivot point. And where's the masseter muscle acting? It acts really close. So in general, in our bodies, the forces from muscles are exerted really close to joints. And we'll talk about the arm in a minute, but that's also true with the jaw. So we don't have muscles out here in the front of our mouth closing our mouth. The muscle's way back here, right? And it sort of fans out up here. I give this guy an enormous temple. But up in this region, right, there's a big muscle that goes underneath this part of the bone and it connects down here on this part of the jaw, and it pulls, right? If you feel your temples, when you chew, you can feel your temples going, right? That's what's happening. This is contracting, it's pulling up. So if you make a simple picture of that, we say, oh, there's an upward force right here due to the masseter muscle. So I'll say force due to muscle. And that's upward force, right? Pulling up on the jaw, right there. And then here's the pivot point, and here's the carrot. So the carrot's exerting a downward force on the jaw, and the jaw's exerting upward force on the carrot. So let's have some upward force on the carrot. Force, I'm sorry, I should be more careful. Let's only draw forces that are acting on the jaw. So this is like a free body diagram right here. So let's make this our free body diagram. Free body diagram. In that case, I only want to have forces acting on this object. So I'll draw the carrot just so you know where it is, but that's not part of my free body diagram. This is the free body diagram of the jaw. And so that means I need a downward force that the carrot exerts on the jaw. Does someone agree with that? So it's force of carrot on jaw. These are not drawn to scale right now. This should be a bigger force, right? The closer this thing is to the pivot point, if it's in static equilibrium, it's going to have to be a bigger force. I should be a little bit careful. The closer it is to the hinge, and the way to see that is by making the hinge our pivot point. So if we, let's see what other forces are acting. Well, there's force of gravity on the jaw. There's mass of jaw times g, right? But this is going to be a tiny force in this problem. I got a fairly big job. It's not that heavy compared to the force my master muscle thinks, right? Unless you've got, I don't know, lead in your mouth or something, right? Chances are you don't have to worry about the force of gravity acting in the jaw. To get full credit on a homework problem or on an exam problem, I will include this force. But if I'm going to neglect it, and you'll usually you'll have some tip off if you neglect it. But I'll state, okay, there's a force of gravity acting on the jaw, but we can neglect it if that's okay. But anyway, and it's acting at the center of mass. This is a pretty complicated structure, so I just made this thing simple and said, let's assume it's uniformly distributed somewhere in the middle. Let's call it the center. Okay? So the downward force due to the force of gravity on the jaw. Are there any more forces acting on the jaw? There's three forces I've drawn. Upward force due to mass muscle, downward force due to gravity on the jaw, downward force due to the carrot pushing down, and let's say it's all I'm chewing on. Are there any other forces acting on the jaw? And this is in static equilibrium right now, right? I'm gritting, I'm chewing really hard, and the carrot hasn't given in yet. It's still sitting there all unchewed, right? No, it's an awful image. So, but there's one more force in the problem. There must be. First of all, is it an upward or downward pulling force, the one that's remaining? I think it's downward. No way. I love the incredulity. Yeah, where is that force? Where's the force acting? Well, what else is the jaw touching? Skull. Where does it touch the skull? The hinge. The hinge is exerting a force on the jaw. It has to be. Because otherwise, what would happen? If you have downward forces on the right of the jaw and an upward force to your muscle, would that result in this thing rotating? Yeah. It'd be going like that. So my jaw's not, right? Painful. If I'm not rotating, I'm just like that. My jaw is pushing down hard on my jaw. Right here. The skull's right here, right? So there's got to be a downward force from my skull on my jaw. Right? These are all on jaw. I'm just being pedantic about this one just so it's clear. So there's a downward force on my skull on the jaw, or if you like, it's a hinge force on the jaw. Right? So in general, the force that most students forget, well, that many students forget, if they're going to forget one, which one's going to be? It's going to be the force at the hinge. Right? There may be other forces at the hinge going sideways or something, right? But we know there's going to be at least a vertical force. Otherwise, you couldn't balance these things out and get no torque. Right? You could still satisfy Newton's second law in the y direction without this force. You could make this one big enough, or this one just the right size, right? So that this plus this equals 0 in the vertical direction. You could do that. But you wouldn't be able to make the torque go to 0, right? Because if you have downward forces on this side and upward force over here, it's going to result in this. Right? That's why I know I have to get downward force over here to counter, like these guys are trying to pull down, but this guy's going to keep that from happening. Right? Don't see that? And that has to be the case. You wouldn't be able to chew. So I mean, I hate to think it, but if you were to break your jaw, or if the connection were compromised somehow, so that your jaw weren't getting a downward force from your skull back here, you couldn't chew anything. Right? It's not enough to have a muscle that's pulling up. You need another force in the back that's pushing down. Right? In order to be in equilibrium, you need at least three forces. And you say, I do have three forces. Yeah, but these guys are going the same way and on the same side. Right? So and forget this one. This one's really tiny anyway. The weight of your jaw does not really play a big role. So for the major forces in the problem, you need at least three. Right? If two of them are going in opposite directions, you're going to get, and they're acting in the same location. So one way around that is if I put the carrot right underneath the muscle, so that they're acting in the same location. Then you only can do it with two forces. So then you have no torque, right? You have the two forces in opposition to one another. But that can't happen because the master muscle acts way back here. I didn't draw my picture as well as it might have, but it's behind the teeth. Right? This guy's got a lot of teeth. He's got a big smile, this guy. But still, even on this crazy drawing, the master muscle is acting to that side, to the left of the backmost molars. So you can't quite put it, almost. Not barely, right? So now we get back to the question. All right, so now what is the force you would do on the carrot? Let's calculate it. And we'll do it by balancing the torques. We can choose the pivot point as our, we can choose the hinge as our pivot point to do that. You might be upset by that. Wait a minute, that means this force is going to get 0 torque. So is that okay? Well, yeah, that'll be okay. Because from this point, we can certainly choose a big enough force here to counter that one so that and this one's not even play a role. Let's just assume this one is about equal to 0. It's not going to play a big role, right? So just these two forces, we can certainly make these balance so that there's no torque. The problem with adding a force here is that maybe you can make these guys balance so that there's no torque when you're over here. But if you choose a different pivot point, say a pivot point over here, if you don't have the force here, then you're going to have non-zero torque. So in other words, if you only have two torques in the problem, if you choose just a special point for your pivot point, yeah, you can make the torque balance. But if you use any other point for the pivot point, now it's no longer balanced. You need three forces for that. But once you have three forces, magically, it works out. Once you've got the magnitude of these three forces figured out, for any pivot point, you're going to find that there's 0 net torque. All right, so let's work it out to this point over here. We'll say Newton's second law for rotations. Our pivot point is at the hinge, right? And now we're going to just write down all the torques. Well, first of all, the torque due to the hinge is equal to 0. And now we've got, what's our positive direction? These are positive. I can use clockwise because I usually do. So do we get a positive or negative torque from the muscle? Here's my pivot point. Muscle acts up. Is that negative or positive torque? Which way is the force acting, up or down? People are pretty sure about that. So is that going to result in and this is my pivot point. And we'll forget the other forces when we figure out the sign of the torque due just to the muscle. If that's my pivot point, is it going to make it rotate clockwise or counterclockwise? Counterclockwise or clockwise? Counterclockwise, which is negative. So I better get minus sign. Am I right? Am I right way around? Force of muscle times what distance? Oh, I didn't tell you what the distance was. Here, I'll just give this a name. I'll call this distance, I don't know, little l. All right? And then we have the sign of the angle between them. But the angle here is 90 degrees because I simplified the problem. I have a horizontal hinge. And, okay, fine. Great. So in other words, I made the pivot point the same height as the places where all the forces act, just to make my life easy. So great. So it's negative Fm times L. And now we're going to neglect this guy. We're going to say that's essentially 0. But now there's a torque due to the downward force of the carrot acting on the jaw. Is that a positive torque or a negative torque about this pivot point? Positive. It's a positive torque. It's trying to rotate the jaw this way. Oops, I should this way. Right? That carrot's trying to open my mouth, if you like. The only one. All right. So here we go. It's going to be F sub c plus F sub